Morning. Let's everybody stand up today since it's Friday, and a lot of people have gotten better at this. First time I had to beg and plead, except you guys. Well, some of these kids are not like the others. Everybody sit down. You don't listen so good. Okay, so today we're going to complete talking about what happens when the memory management unit asks the kernel to help it translate a virtual address. And we'll talk about the kernel. So now this, for the last week or so, we've been talking about memory management. We've been talking about a lot of what the hardware does. So today we're going to start talking about actually what happens when the kernel gets involved, right? So this is the part that we're more interested in as operating system designers, right? And we'll start talking a little bit about towards the end about what happens when we run out of physical memory, right? So one of the things we liked about this virtual memory abstraction was that it allowed us to play games with the actual location of memory that was pointed to by virtual addresses. So today we'll start talking about a little bit about one of those games we could play, and then next week we'll talk about it more, okay? So we still have midterms to pick up. If you haven't picked yours up, please, I'll be upstairs after class or come to office hours. And at this point, you should really be on to doing the assignment 2 implementation. If you're not there, then you're behind. And you're getting more behind as time goes on, right? Because the amount of work in front of you is the same, and the amount of time you have is decreasing, right? So the other thing is, so the assignment 2 design documents, what we're going to do this year is, you guys, it's similar to the code reading questions. You have 2 shots. And you'll get so you're welcome to receive feedback from the TAs and then resubmit the design. However, in the past, we could have set it up so that you had to do a design before you started on the implementation. Instead, what we're going to do is, if you come to office hours, right, from this time forward, I will tell the TAs this, and you are asking for help with implementing assignment 2, you must bring your design document with you, a paper copy of your design. Right? So if you don't have a design, the design hasn't been graded, that we're not going to help you with the implementation. Right? So please don't start with the implementation and try to work backwards. Right? Until you have a design, the TAs won't help you in office hours. And part of the reason we asked you to write this design in the first place is so that the TAs can have some idea of what you're trying to do. Right? So the first thing, or one of the things they may do if you have a question is look at your design and try to figure out, are you guys totally, what are you trying to accomplish? Right? Because for assignment 2 and assignment 3, the code bases get really big. Right? With your locks and CVs, I or the TA can sit down, and in about 30 seconds, we can look at your locks and CVs and tell if they're right, right? With assignment 2 and assignment 3, if I had to sit down and read your code, it would probably take me a good half a day to figure out if it was right, right? So just coming in and being like, here's these 3 lines of code that aren't working, I mean, they're going to be like, I have no idea what's going on, right? I haven't seen the other 1,000 lines of code that you guys have written for this assignment that are potentially part of the problem, right? All right, so any questions about paging and page structures, or the page structures that we got through on Wednesday? OK, so let's do a little bit of review. One of the things we liked about paging was that it maintained some of the nice features of segmentation, right? So what were some of the pros of our paging-based approach, right? So we came to paging after we noticed problems with base and bounds. Base and bounds was really just kind of a straw man because it was really broken. And then we came up with this nice idea of the segments. But then after we thought about segments for a little while, we also realized that segments had some issues, right? And then paging came along, and paging seemed to offer some solutions to some of these problems. So what were the things that we liked, some of the things that we liked about paging? Tim? You cannot have, right, so this is great. No more external fragmentation, right? My page allocator becomes extremely simple. I will never be able to not satisfy a page allocation request because of external fragmentation, because all my units are the same size, right? So that's really, really nice, right? This was this problem we ran into with segments where if the segment got a little bit bigger, then maybe I would have to move it. I might not be able to find enough space, and I could move things around to address the external fragmentation, but that would start to get ugly and cause a lot of overhead, right? So yes, no external fragmentation. That's fantastic. Sumit, what about something else? Why?
You have
Well, I don't know. So that's a good question. I don't know if address translation is actually faster or not, right? We talked about a way to make it fast, right, by stripping off the virtual page number and using content addressable memory to very quickly find a translation, right? But I would argue that with segments, there's probably some equivalent hardware logic that might help us do that as well. Jeremy? Okay, okay, so yeah, maybe the translation is a little bit easier. That might be fair, right? Partly because so what makes it easier, right? Potentially. Yeah, I had this nice bit masking thing I would do it, and I would argue maybe that the fact that remember what I'm essentially doing is I'm fixing the size of this segment. So now my segment size is the same, and that might make things a little bit easier, right? But we're talking about hardware here, so we can make that pretty fast. Paul. So right, so one of the pros of paging that we inherit from segmentation is we can essentially inherit the protection that we apply to a segment, right? So if we say a segment is read-write, the way that maps down to paging is that all the pages in that segment need to inherit those permissions. So that's kind of a nice feature. What else? Greg, you have something. Yeah, basically, right? So the bounds is fixed, right? So I don't have to necessarily check the bounds, right? Again, what I did before, if I have powers of 2 pages, I can strip off the page number pretty easily and then just slap the offset back on at the end, right? Okay, so I can organize and protect regions of memory appropriately. This is something from segments. Okay, so nobody got this one, right? So pages are better fit for our address space abstraction than a segment per portion of the address space, right? Because having one segment meant that there was this potential for a lot of internal fragmentation, right? A process might have a huge heap that's grown over time where it's done dynamic allocations, but large portions of that heap might not be in use at any particular time. But with segments, I have to have the whole heap resident in memory or not, right? So at segments, I make this decision about whether or not to have a valid segment on a segment-by-segment basis. Now on pages, I've reduced the granularity, right? And again, no external fragmentation because I have a fixed allocation size. So this is very nice, right? What about cons of paging versus segmentation? What's one sort of significant potential problem here? AJ. Yeah, so I can potentially map a smaller amount of memory with the same state in the MMU, right? Because with segments, right, as the segments got bigger, the amount of memory that the MMU could map for a given number of segments got bigger too, right? So if I have these huge segments, let's say I have 4 1 gigabyte segments that are mapped in the MMU, now I can map 4 gigabytes of memory without involving the kernel, right? With pages, because I've chosen a fixed allocation size, and because that allocation size is usually pretty small, like 4K or 64K, right? The amount of memory that can be mapped by the TLB is reduced, right, potentially. Jeremy, you had a comment? Yeah, so that's the problem, right? As I reduce the amount of state, as I reduce the amount of virtual memory that the MMU can potentially translate without asking the kernel for help, I end up having to ask the kernel more often, right, for the same workload, right? Why does this end up not being so much of a problem? Or what feature of process behavior helps us out here? Amit. Locality, right? So, I have to do these per page hardware translations. The hardware is going to help us out. The amount of memory I map is going to go down. But the nice thing is that when processes are running, because of how things are laid out by the compiler and other things, locality is, I see a lot of address locality, right? So I see a lot of use of 1 or 2 pages, right, during a certain part of a function, and then I might jump to another part of the code, and then my locality moves, right? But the address locality helps a lot, right? If my addresses were randomly temporally distributed across the entire address space, then small TLBs wouldn't work as well as they do, right? But they're not, right? Just because of how processes behave. And the other problem that we're going to talk more about today is now I need this per page operating system state. So the operating system now has to store some information about every virtual page and every address space for every process on the machine, right? Every valid page in any address space that's created by any process The operating system has to have some state, and I have to be able to kind of find it rapidly when I need it, right? So when the MMU asks me for help, I want to do things as rapidly as possible to avoid sort of slowing things down, right? All right, so when the MMU asks for help, when it says, hey, the process tried to access this virtual page, and I don't know how to translate that to a physical page, what state do I need to be able to recover? Dan? So the MMU is going to tell me, here's this virtual page number, right? Here's the address that caused. So first of all, what's going to happen here, right? The address is not in the TLB. The MMU is going to do what? Sugar. It's going to cause an exception, right, of some kind, right? It needs the kernel's help, and so we're going to follow the standard exception handling path. We're going to enter the kernel. The kernel's going to, but then what does the kernel need to know, right? So as Dan pointed out, it needs to know the address the call is the fault, right? What else do I need to know to be able to translate the address? Satish? No. You want to help him out? What's that? The process ID, right? And does the kernel know this? Yeah, because it scheduled the process, right? So I'm in OK shape there, right? What else, Jan? I'm just working my way across the room today. Hui Kyung, you want to help us? Not sure. Greg. What's that? Memory. What about memory? Okay, yeah, but I mean, on some level, right? Remember that yeah, I'm gonna track that over time. But really, what I'm trying to do is just get an entry into the TLB, right? Sumit.
What type of operation is trying to do?
Yeah, so I might need to know. So this is the information I need to store, right, for each virtual page, right? I need to know where it is, right, so that I can put an entry into the TLB. It's kind of automatically associated with the process, since all these data structures we're going to talk about for storing virtual to physical translations are per process data structures, right? Why are they per process? Harish? Yeah, because virtual addresses are meaningless without a process ID, right? So it makes no sense to talk about what a virtual address means without talking about it in terms of a process context. And so all these data structures we talk about are per process, right? Keep that in mind when we start talking about how to design them, because the amount of space that they take up also scales with the number of processes, right? I need one of these page tables or a page state storage structure of some kind for each process, right? And the other thing I want to be able to do, and the thing we'll talk about today, is when the TLB requests this information, I want to be able to find it rapidly, right? Because why? Sean?
Because it slows down the process.
Yeah, it's slow. I mean, I always want to do things fast in the kernel, right? There's no reason to do anything unnecessarily slowly. But when when this happens, I'm already slow, right? I've already hit a case that I don't want to hit because the TLB was already unable to translate that address automatically, right? The TLB didn't know about it, have to ask me for help. At that point, I've already encountered, or the process has already experienced a large amount of delay, right? And I don't want it to make it worse, right? This is well, anyway, let's see if anybody can answer this question. Manish. This is a reading the title of the slide type question. Robert.
Page table entry.
I'm going to go with page table entry, yeah, for 1,000. Yeah, that's what it is. And we refer to these colloquially sometimes as PTEs, right? This stores a single virtual to physical, or potentially it stores, sorry, I misspoke. I know that almost never happens, but this stores information about a virtual page, right? That information might include, what types of information might I need to find out about that page? Simon. I mean, need to know some permissions, right? So what types of what types of memory operations are valid for that page, right? What else? Alyssa. What's the most basic? So the page is like some, some memory or some content somewhere, what do I need to know about it? And especially like when I'm trying to load the TLB. Where it is, right? So location, and that location can be in memory, and we've been talking primarily up till now about pages that are being in memory and translating virtual addresses to physical memory addresses. Today we're going to start talking about where else pages can go, right? But wherever pages go, the operating system needs to know where they are, right? And so this data structure needs to keep some state about that, right? What else could be in there, Jen?
Whether or not it's a valid page?
Yeah, sometimes we keep that in the page table entry, and sometimes we just don't have a page table entry for pages that are invalid, right? It's more common that we don't have a page table entry, because if we had to have a page table entry for every page, regardless of whether it was valid or not, we'd have to have a lot of page table entries, right? Because address spaces are big, most of them are unused, right? All right. And again, we talked a little bit about how we can jam this into one 32-bit machine word, or maybe a 64-bit double word, right? So I have some number of bits for the location, some number of bits for permission, a valid bit. So the valid bit, actually, this is a good segue to Jen's answer. So the valid bit usually doesn't say that the virtual address is valid. It usually references, is the page in memory, right? So that's a different type of validity, right? So sometimes this valid bit is used to interpret the location, right? If the valid bit is set, the location is a physical page number, right? Sorry, this should be physical page number. And if it's not, it should be, it needs to be something that allows the process to find the contents of this page, right? And then sometimes I might want to store some information about whether this page has been referenced, right? And we'll talk a little bit about, so let me ask you one question for people who are kind of following along. So does the operating system see every access to a virtual page, right? Robert's saying no. Why not? Yeah, I don't want to see every access, right? If I saw every access, I'd have a really slow system, right? Or I'd really have a problem with my address translation. So most of the accesses are done completely transparently, right? So keeping up-to-date information about which pages are used is actually a little bit of a challenge, because the MMU hides a lot of information from me on purpose, right? I don't want to know, right? If it had to interrupt me and say, hey, the page was used, page was used, page was used, things would slow down even more, right? Jeremy? Oh, OK, yes. So we'll save that question for the end of class, right? MMUs, poking around in kernel data structures. Sounds like a terrible idea. Turns out to be very common. And we'll talk about that later, right? OK. So this was our review of what happens when I need to find some information about a page, right? The process is trying to store to a virtual address. The MMU doesn't know anything about that virtual address. It causes an exception in order to allow the kernel to address the situation, since the MMU doesn't have anything else that it can do. And the kernel really needs to be able to find this information rapidly, right? So there's two, as I said before at the end of class on Wednesday, there are these two requirements for the data structures that we use to store information about how to translate virtual pages to some information about where they are and what to do, right? The first is speed, right? So obviously I want to be able to find this information as fast as possible, but the second requirement is compactness, right? Because if these data structures live in memory. So if the data structures, if you had a machine where it was like, I can do really, really fast virtual to physical address translation, unfortunately, my data structures consume 2 gigabytes of your 2 gigabytes of memory, right? Then that's not going to be a super useful machine, right? So on some level, any memory that's devoted to these data structures becomes overhead, right? Overhead that the system has to deal with, right? As these data structures grow, everything's going to slow down because there's less physical memory on the system, potentially, right? All right, any questions about this before we start talking specifically about how page tables are implemented? All right. So again, a page table is a data structure that's used to do this mapping quickly, right? So when the TLB, when the MMU interrupts the kernel and says, I need help mapping a virtual page number, I want to be able to find this information, right? And we talked before about the fact that every process has a separate page table because process virtual addresses are exactly that. They're meaningless outside of a process context, right? Because remember, our virtual address abstraction, our address space abstraction, gave every process this really nice, identical, uniform view of memory, right? But it means that there's a lot of overlap between the virtual addresses that are in use by any given process, right? All right, so I'll talk about a couple different ways of doing this, and we'll talk about some of the trade-offs, right? So one approach, right, which is kind of our, I'll just give a hint, this is kind of the straw man approach, potentially, is a flat page table, right? A flat array of page table entries. So let's say our page table entries are 32 bits, right, 4 bytes. And I have 2 gigabyte virtual address spaces. So what I could do is I could just say, hey, for each virtual page in the address space, I create one big array, and I use the virtual page number as an index into that array, right? And in that array, I store the page table entries, right? So this is kind of a nice idea. It's very fast, okay? So here's my flat page table. Here's my address space, okay? And here I've, again, as usual, I've marked the portions of it that are valid, and maybe I have a couple threads running here, so I have 3 stacks, one for each thread. I have page table entries, right? So I need a page table entry for each valid virtual page, right? I think on this slide I've decided that the code is actually taking up two virtual pages. You can tell because it's thicker. So I have these 6 page table entries for my 6 valid virtual pages. And this is basically how I do it, right? I use this flat page table entry. And actually what would happen is that this would be the page table entry, right? I wouldn't use a pointer to find the page table entry. I would just store the page table entry directly in the page, right? But essentially there's just a one-to-one mapping between virtual pages and this flat page table structure, right? Do people understand how this works? This is a little bit different maybe than if you're used to using things like Java arrays or whatever. C arrays are big data structures that sit there in memory, right? And all I'm doing is I'm using this virtual page number, right? Let's say this is virtual page number 3, right? It wouldn't be, it'd be something bigger, and I just use that directly as an index into my flat page table. Does this make sense? Raise your hand if this makes sense. Just want to make sure everybody's with me. Sweet. All right, so this is nice, right? It's very fast, okay? Wembley is still raising his hand. Exactly. The virtual page number is the top 20 bits, right? If I'm using 4K pages. If I'm using bigger pages, then it would be a smaller number of bits. If I'm using fewer pages, it would be a larger number of bits, right? I think Wembley's on to what's wrong with this, right? Well, it's a good question. How many entries? Let's say I have, let's say I have 2 gigabyte virtual address spaces, right? I have 32-bit addresses. How many entries does this flat page table have to have? The top 20 bits of my address are the virtual page number. It turns out that I would need 2 to the 10th, which is big. No, sorry, 2 to the 19th. Oh, sorry, I was about to say, that's not that big, actually. Yeah, so I would need, roughly 500,000, right, to map the entire address space, right? And this is the problem with this approach, right? My lookups are 01, right? All I do is I take the virtual page number and I use it directly as an index into that array. Great, right? My compactness is terrible, right? So now again, I have potentially 4 megabytes of physical memory that I need to use per process, okay? And then here's the other thing that's interesting, right, that we talked about before. So we said the nice thing about our 4K pages was that we never had to do, we had no external fragmentation, right? But if in certain cases, the kernel can actually access physical memory directly, right? It has some sort of direct mapped access to physical memory. And so, for example, on your system, on OS 161, where you guys put kernel data structures, they actually do have to be contiguous, right? So there's potential, like if you did this on OS 161, you would have to find 4 megabytes for each process. And not only that, I mean, first of all, you wouldn't be able to find 4 megabytes very often, right? Because your system might have a total of 8 megabytes in it, right? So congratulations, you can support 1 process, right? But not only that, it would actually have to be contiguous in physical memory. So there's certain cases where kernel data structures have to be contiguous. And then the worst thing about this, right, is most of this is completely unused, right? So for example, You know, here's a case, and you know, I'm going to have similar mappings for these other 3 pages, and maybe one for this guy. But you know, the sparsity of this data structure is a function of the sparsity of my address spaces. Right? My address spaces are sparse. The usage of this data structure also be sparse. Right? So this isn't a very good idea. Right? All right. So let's look at a different approach. Right? So, and this is actually something that you guys could think about implementing. Right? For assignment 3. So in this approach, what I do is I have just a list. Like I have a linked list of PTEs. I have some sort of list structure that grows with the number of PTEs. And when I need to look up a virtual page, I just search this list until I find a page table entry that matches the virtual page number I'm looking for. What happens if I don't find a virtual page, a PTE that matches the virtual page number that I'm looking for? What might I have to do at that point? Tom? No, this is the kernel. I am the kernel. I've already been interrupted. You know, the MMU said, hey, I don't know how to translate this virtual page, and the kernel looks in its data structures and can't find a translation. What do I need to do? What's that? I might have to kill the process, right? The process, this might create, you know, that segmentation fault that some of you guys have seen, right? It means that the process tried to access some memory that I haven't given it permission to access, and I have to just kill the process at that point, right? I can't complete the instruction, right? The loader store has nowhere to go, right? So I might just have to stop the process. Okay. So here, this is like the big fun diagram day. Here, you know, I have some, you know, I have a PTE for each virtual page, right? And I just organize them into this nice list, right? And if I need a new one, you know, I tack it on at the end, and you know, this list kind of grows with the number of, the size of this list grows with the number of PTEs that I have, right? You know, this is your classic. How many people have implemented a linked list in C? Good. All right. So, and here what I do is, you know, let's say that the MMU causes an exception, right? And I'm looking for the virtual page corresponding to this part of the process's address space. I just kind of look through my linked list of PTEs until I find one that matches, right? And then I can use the information in the page table entry to, you know, to load the correct virtual page number into the MMU, assuming that the page is in memory, right? Or do something else, right? But I found the information about this page that I need to have, right? I kind of want to like slow down and just let you guys savor this, because I think this took me like an hour to do when I did this. It's green. Shocking. Okay, so let's talk about speed, right? So what is the what's the big O notation for this, right? If I have n valid pages in the address space, how long is a typical search going to take? Satish. Yeah, it's O of n, right? Because, you know, so does this make sense? I'm not an algorithms person, but I break out the big O notation once in a while just to impress people. All right, but what about compactness, right? How fast does this data structure grow? Let's try to get this. Grim. I have n valid virtual pages. You can use big O notation. N squared, n times n. So we have a vote for n squared. Andrew, you want to? Does anybody nominate a different candidate? Yeah. O of n, right? 4 bytes, or whatever the data structure is, the size of the PTE data structure, and that just grows with the number of pages in my address space, right? So it's O of n, right? If you go back here, I don't think I use big O notation, but this is just O of huge, right? It's a constant, right? But it's a huge constant, usually. It's a constant that's way bigger than we want it to be, right? But actually, here's a good question, right? So the size of this data structure, here, the constant size of it is really is dependent on something, right? What is dependent on? I'm ignoring you, Jeremy. Peng. There is something, so it's not actually a constant. It's dependent on what? Jen. Page table. Well, this is the page table size, right? But the page table size for this flat page table is determined by. Sarah, you want to help her? AJ. Okay, so that's true. That's not what I was thinking of, but that's one part of it. And then what else? Amit? Nope, that's not true. Mukta? Yeah, and that's determined by what? The number of bits that constitute the virtual page number is determined by what? Yeah. The size of the page, right? So here, as the page size gets big, this data structure gets smaller because there's fewer pages in the address space, right? So it's essentially the address space divided by the page size. So it goes up as the address space gets bigger, down as the page size gets bigger, right? All right. I just wanted to show you this again, really. That's why I went backwards. OK. All right. So this is O of n. That's nice, right? And this is, especially for a small number of pages, this is a completely valid way of translating page table entries, especially if you, for example, were forced by some cruel person to actually implement a small virtual memory manager for an assignment for some terrible class, right? You could do this, and it would work fine, OK? Just saying, right? Yeah, there we go. And this is, I should just pause here and point this out, right? So especially when you're doing systems programming, there is one of the lessons that we try to impart, and we hope that you're learning throughout the class, is don't design something overly complicated before you know you need it, right? So it turns out, I did this when I did these assignments, and it was like, oh yeah, cool, I'm going to do multi-level page tables. It's going to be awesome, right? It's just like, who cares, right? There's 4 pages in the address space, right? On OS 161, or like 10 maybe, right? If you have a big process. So, the linked list works pretty good, right? And it's super, super fast, right? All right, but let's talk about real systems and the type of data structures that they use, right? And hey, like these aren't super complicated either, right? It turns out. So the approach that's used on a lot of systems is what are called multi-level page tables, right? And what multi-level page tables do is they try to balance the two approaches, right? So the nice thing about the first approach was that it was fast to do the lookup, right? Single operation. The nice thing about the second approach was that it was small, right? So location, speed and compactness, right? So I've seen the extremes, right? I've seen the extreme in speed, worst, best speed, worst compactness, and I've seen the best compactness, potentially worst speed. I mean, you could make it slower if you wanted to by just doing dumb things, right? But that's really the slowest speed of a valid page table. Yeah.
What about just the regular binary search?
That's kind of what these are, right? So let me describe this. That's basically what we're going to do here, right? So what we're going to do is we're going to build a tree-like data structure. It really is a tree that are used to again map these virtual page numbers for a PTE, right? And what we do is we split. So in the first case, what we did is we used the entire virtual page number as an index. Multi-level page tables split the virtual page number into separate parts, which are used as separate indexes in the different depths of the tree. So I use one part in the first level of the tree, and then the second part in the second level. It's basically a binary tree, right? So I have a graphic for this. Don't worry. So we'll go back and forth between these two slides, right? So a common way to do this with 4K pages, right, is to observe the fact that there's all sorts of nice things that happen here all of a sudden with 4K pages, right? So my virtual page number is 20 bits, right? If I split that into 2 parts, 10 bits for the top half of the index and 10 bits for the bottom half of the index, right? And also keep in mind that on 32-bit systems, pointers are 4 bytes, right? So what works out nicely here is that my top level of the tree needs 2 to the 10th entries, because my index is 10 bits. Each entry is 4 bytes. So what turns out is that it's 4K. And then all of the second levels are also 4K, which is nice, because pages are 4K, right? So now I have a data structure that I can build where each piece of it is in a unit of a page, right? So maybe that's why people like 4K pages. I actually think if you make 8K pages or 2K pages, this stops being so nice, right? But 4K pages, it just all works out really nicely, right? All right, so we'll come back to that slide to talk about this in a minute, but let me do the graphical example first, right? So every process requires a first level page table, right? No matter, even if I have one page in my process that's valid, I always need a first level. I will always have a first level table and at least one second level table, right? So what happens here is I use the top 10 bits of my virtual page number here as an index into my first level table, right? The first level table is used to find the second level table. So the first level table needs to, for this index, needs to have a pointer to the second level table that contains the rest of the information about this virtual page number, right? And then I use the bottom 10 bits as an index into my second level table. And at that point, either the 4 bytes in the second level page table are the page table entry, or if my page table entries are larger, I might have them somewhere else, and I have a pointer to them in my table, right? So I use the top 10 bits as an index in my first level table. I use the bottom 10 bits as an index into the second level table that I found using the first level table, and then I find my PTE. Okay? Let's back up, and we'll go through this again, right? So. Yeah, so exactly, right? So the idea is, in the worst case, right, if my entire address space was mapped, I would have essentially the same amount of mapping as the flat page table, right, plus 1 additional page table for my first level table, right? So as the amount of virtual address space that's used by my process grows, right, this can potentially get as big as that flat table, right? But it usually doesn't, right? Why is that? So for example, for this process, how many again, every process always needs a first level page table, right? I can't translate a single address without a first level page table. Someone want to guess at how many second level page tables would this process have? I hear 6. Does anybody want to put up a different number for vote? 6. Not a huge fan of 6. Yeah, the number of second level tables, right? Or the number of valid entries in the first level table is the same thing, right? Spencer, you want to make a guess? What? 4. Okay, okay. Getting warmer, right? We're bracketing the target. Anybody want to? I hear 5. Okay, so yeah, so it really depends on how these pack together, right? I definitely remember the question is how much virtual memory does each second level page table cover, right? It turns out that second level page tables have 2 to the 10th entries, right? Each entry is 4K, right? So if I'm doing my math correctly, what happens is each second level table maps 4 megabytes of virtual address space, right? So I'm betting you for this silly little process here, its code is it might be less than 4 megabytes, right? So let's say that its code is less than 4 megabytes. So now I need 1 second level table for its code, right? Far, far away from the code is this heap, right? So is the heap going to be on the same second level page table as the code? No, the heap's going to need its own page table. But until the heap gets to be 4 megabytes, the heap can do with 1 second level table, right? So now I'm up to 2. And then again, I'm going to say here that I think these stacks are far enough apart that they're not going to land in the same second level page table either, right? But I'm also going to say that they're not 4 megabytes. I mean, if they were really as wide as they are in this figure, they'd be 4 megabytes, but they're not, right? So I have 1 second level table for this guy, 1 second level table for this guy, 1 second level table for this guy, and I have 5 tables in total. Does this make sense? Part of what's nice here, right, is that I'm getting a constant time, Jeremy, I'll come to you in a sec. I'm getting a constant time overhead for my search, right? Remember, my searches are still constant, right? I have 2 lookups rather than 1, but it's still constant time search. But on some level, this expresses better the sparsity of the address space, right? Because, for my, and remember, each one of these tables is 4K, right? So with 5 tables, plus the first level table, I have 6 page tables times 4K. It's 24K total, right? To map the entire address space for the process. For my flat page table, I needed 4 megabytes of page tables to map the process, right? So again, 24K, right, which is, like 3 orders of magnitude better in terms of the size of these structures, but I still get constant time lookups. Jeremy, your question?
So you're actually
Yep.
Would it make any sense to just make like a binary search tree that has children for each node?
I don't know. I have.
Then it would only require the same amount of space as the linked list would, but it would search faster than the linked list.
Yeah, I mean, there probably are other. I'll have to think about that more. There probably are other data structures you could use to solve this problem, right? The nice thing about the nice thing about this, for example, is, especially with 4K pages, everything's in units of 4K, which is nice, right? Everything is bit masked indexing, right? So I take the virtual page number, I strip off the top 10 bits, and I just use those as an index, right? I strip off the second 10 bits, I use those as an index, and then I find the physical page number if it exists in memory, and then I whack the offset back on, and I'm done, right? So this has this kind of appealing simplicity to it, right? I don't know if I did another example, right? So my speed again is constant, right? My lookup time is constant here. It's roughly potentially twice what it would be, assuming everything's in memory, right? It's potentially twice what it would be for the flat page table, but my compactness is, it's probably O log n or something, but it's much better than my flat address space, right? Like I said, for this simple example, I've achieved 3 orders of magnitude smaller page table size, which is great, because again, my page tables are competing for processes for memory, right? So I don't want them to be huge, okay? All right, let me pause here for a second and see if there are any questions about multi-level page tables. Do some reviewing this on. And again, this is something you could implement for assignment 3, but you don't have to. There are other ways to do it. You could do, and Jeremy, if you want to try a binary tree, go for it. Just make sure it's in your design so we have some idea what you're trying to do when you come off. All right, so let's do a few other things today. So next week we're going to start talking. So I've been hinting, right, throughout that pages might be somewhere other than in memory. And on next week we're going to talk more about where, so first of all, I think you guys have some idea of where pages go, right? Where do the pages go when they're not in memory? Who knows? Just some happy place, right, when they come back. So again, I might have some case where a process maps enough memory in its own address space to exhaust the physical memory on the machine, right? And then if I try to grow, let's say the process allocates a big data structure and wants to grow its heap, right? Now what do I do, right? And at this point, right, I really have two options, right? I can fail. And this isn't as completely nutso as it sounds, right? So for example, as far as I know, the current versions of Linux that run on Android devices do not do swapping. If you run out of memory, they just start failing stuff, right? They might try to find some stuff to kill so that they can free up some memory, but they don't move stuff to disk, right? They just say you've got as much memory as you've got. If you try to run an app and you're out of memory, it just doesn't run, or I try to find some memory somewhere and kill things off, right? So I don't have to actually succeed in this case, right? I can just fail. However, what we usually like to try to do is to create more space, right? So can I find a way to free up some memory? And this is kind of, remember we came back to those 4 requirements for my memory allocator. One of them was reclamation, right? I want to be able to reclaim memory. And the thing that we're going to do here, right, is we're going to use the fact that I have this mapping that the kernel controls as a way of being able to trim the amount of memory that's in use by a process behind its back, right? At some point, I allowed you to use a virtual address, and I pointed it to memory, right? I gave you some memory to use, okay? And so from the perspective of the process, right, I was using that as a virtual address, and it pointed to memory, and that was great, right? I was happy. The requirement for doing this is that if I'm going to take some memory away from the process, the point at which I have to restore it is the next time the process uses the virtual address, right? So again, what I don't want to do is violate the memory interface or violate the assumptions that processes make about memory, right? When I use a virtual address, it should behave like memory, meaning that I should be able to do loads and stores, they should be reasonably fast, and it should retain the contents that I put there, right? So if I start up and I load dead beef into some part of my address space, and 5 days go on, or 5 hours or whatever, and I do a read, I should still get dead beef, right? Nothing like storing dead beef for long amounts of time. Hopefully it's somewhere cold. So again, the idea is that the operating system can repurpose this memory. It can reclaim it, right? And we're going to talk about exactly how I do this. But I have to make sure that I preserve the contents, right? Otherwise, I'm going to fail, right? So the typical place that we put memory when I want to borrow it from the process is I move it to disk, okay? This, and we call this process of moving pages back and forth transparently behind a process's back, we call this swapping, right? And again, if you set up a Linux system, you've created a swap partition, which is used to enable swapping, right? It's the place where pages go when they're not in memory. One of the consequences of this, though, right? So what have we always been worried about with the disk? It's really slow, right? And so the great thing about moving a page to disk is that I can create more memory, right? Yes, I have an extra page, you know? I knew that process wasn't using that memory. I moved it to disk, and now I've got this extra page that I can give to a process who's asking for it. So that's fantastic, right? The problem here, and the thing that makes this quite an interesting design challenge and an interesting systems challenge, is that there's a huge overhead to moving it to disk, right? So I have to, you know, take all the contents and write it to disk, and disk is really slow, right? And we'll talk next week about, you know, cases where if I don't swap very well, I can, man, sometimes I feel like I wrote these slides. So the goal of swapping is to enable the system to feel, right, to feel to you as the user as if the amount of memory in the system is actually not the amount of RAM that you bought, but the amount of RAM plus the size of the swap file, right? So if I have, you know, 4 gigabytes of RAM and I take 4 gigabytes of my disk and use it as swap, what I want is the system to feel like it's got 8 gigs of RAM, right? That's awesome, right? It's like twice as fast, maybe. If I don't do this right, what will happen is that it will make the system feel, actually it could be worse than this, right? I should have strengthened this. If you do swapping really badly, what will happen is it'll make the system feel like it doesn't have any memory at all. And all of your memory is as slow as the disk, right? So if I do this right, I can I can make your memory look much, much bigger, and I can make it all look like memory. If I don't do it right, I basically look like I make your system look like memory is a disk, and it's as slow as a disk, right? Which is super slow, okay? So we're going to talk on Monday about how to do swapping, right? Algorithms for swapping, and essentially this boils down to when I need a page in physical memory, how do I choose a page so that these trade-offs work out okay? If I choose the wrong page, I'm going to make memory look as slow as disk. If I choose the right page, I'll make disk look like an extension of memory and just as fast, right? And we'll get to this on Monday. So I will see you guys on Monday.